Hello, in this video we will go through the solution of Stokes' first problem.
Stokes' first problem is the problem in which a boundary is set in motion at a certain point in time. And so we could sketch this by essentially drawing a semi-infinite domain in the y direction and setting up a wall at y equals 0, okay? And that wall, at a certain point in time, which we will label as t0, starts moving in the x direction at velocity capital U. So I'm going to draw this to be the x direction, and like an example velocity profile here, we expect the velocity to be something like this, like sort of maybe exponential decaying like this. And this is the flow that we are going to solve for. So first of all, the approximation in this problem are as follows. So we assume that the flow is only one-dimensional. It only travels, the fluid only travels in the x direction. So we are going to make the approximation that this is a one-dimensional flow. In other words, we're setting that u, the velocity vector, equals u as a function of y and t in the x direction. We are going to say that the velocity does not depend on x. We'll see in a moment that this is not a necessary hypothesis to solve for this flow, but just to save some time, we'll make that hypothesis here. And last but not least, the flow is entirely driven by the motion of the boundary. Well, in fact, by friction, right? But this is the motion of that boundary that is going to drive the flow. There is no pressure gradient or other volume force in this flow, or to drive it. So let's just write down the whole problem. So let's just start off by the boundary conditions. They are immediate because they are sort of core to this problem. So the boundary conditions write that the velocity u, I'm just going to write down that component of the velocity now that we've assessed that the flow is one-dimensional. That velocity here is capital U at y equals 0, and we also can say that the limit when y tends to infinity of u has to be equal to 0. These are my two boundary conditions. Additionally, well, to discriminate from an established flow and to essentially look at the setting up of this flow, we are also going to impose an initial condition. And that initial condition is that u at t equals 0 has to be 0 everywhere, independently of y. Okay, so these are our boundary conditions in initial condition. Now let's look at the equations for this problem. So first of all, we'll have the incompressibility condition, as usual, condition. And well, let's just write down these equations in 2D for now and look at what, sort of approximations come out of them. So if I write it down in 2D, I've got du by dx plus dv by dy equals 0. And you can observe there that because there's no flow in the y direction, okay, there's no v velocity, this is automatically 0, and therefore this leads that du dx equals 0, which in essence means that u does not depend on x. Okay, so and that's why I took out this x component, this x dependence here out of u. Is because, well, we'll automatically know that this is not a, this will not, because there is no velocity in the y direction and the fluid is incompressible, there has to be no dependence of the x component of the velocity with the x direction. And so this is automatically satisfied. So, well, there is no need to worry about this in the future. Then the next equation that we need to solve in this context is the Navier-Stokes equation. And the Navier-Stokes equation, well, I'll just write it down in two-dimensional form and in component form. So that's going to be rho du by dt plus u du dx plus v du dy equals minus dp dx plus mu d2u by dx squared plus d2u by dy squared. I can also write down the same equation for the v component of velocity just for the sake of completeness. So that's going to be du dv by dx plus v dv by dy equals minus dp dx plus mu d2v by dx squared plus d2v by dy squared. And that's my Navier-Stokes equation written in component form. This equation, because of this assumption here, simplifies dramatically. In particular, I can write that the first equation here, u depends on t, and we're happy with that, but u does not depend on x, and there is no v. So my left-hand side just becomes rho du dt. And on my right-hand side, I've still got my gradient of pressure, but this d2u by dx squared goes away, and I'm left with mu d2u by dy squared. So that's for my first equation. Now my second equation, because v is 0, becomes a simple equation on the... Oh, this is a y here. This is a dp dy. Becomes a very simple condition for the pressure, which is that there is no gradient of pressure in the vertical or sort of wall normal direction. So dp dy equals 0. So these are my two equations. Now, of course, this means, in a sense, that p is only a function of x, right? It's not a function of y. But in fact, because this flow is not driven by a body force, there is no body force that is applied onto this flow, then that gradient of pressure can be taken off of this equation. Okay, so if we just look at this, send this into the left-hand side, we get on the left-hand side rho du dt plus minus mu d2u by dy squared. This is only a function of y. And on the right-hand side, we have dp dx, which is just a function of x. We can differentiate this with respect to x and find out that this dp dx is just a constant that does not depend on x. In other words, because of that, it means that we have a constant volume force acting in the horizontal direction. And because I said that the flow is not driven by any volume force, it's only driven by the motion of the boundary, then we just we will just set that dp dx equals 0. And in other words, the only equation that we have to solve here is rho du by dt equals mu d2u by dy squared. And I can rewrite this down by introducing the kinematic viscosity. So du dt equals mu d2u by dy squared, where nu equals mu over rho, right? It's the kinematic viscosity. Okay, so based on this, we just have these two boundary conditions, this initial condition, and this equation. And I'm going to label this equation 1. Okay, so to solve this equation, there is a set of methods that can be tried, essentially separation of variables, similarity solutions, and so on and so forth. You essentially either have some intuition about which method is going to work in which case. It's pretty much most of the time these boundary conditions and the initial conditions that are going to determine which method works or not. So be careful, and when you get used to solving, when you get experience solving these equations, try and remember what kind of boundary conditions yield to which method. If you don't have this experience or this intuition, just try one, and if it works, then jackpot. And if it doesn't work, then you will, well, the reason why you can diagnose that it doesn't work is because one of these conditions cannot be applied in the end, and will lead to a sort of contradiction. So 1 equals 0, for instance. So in this case, well, the method that will work due to these boundary conditions is the similarity solution. So let's look for a similarity solution. And it's a good exercise to build up this experience, to not try the similarity solution method, but rather to try a different method and see why it fails. So the similarity solution in here, we will write that u, which is a function of y and t, and we'll write this out as f of eta. So f, a function of eta, where eta combines both y and t. So I'm going to write down that eta is actually of the polynomial form yt to the a. The reason why we want a polynomial form is because these are partial derivatives. And so we will have powers of these quantities going through the derivatives. And so I'm just writing t to the a with a to be determined, okay? A to be determined. Okay. So before doing that, before being able to determine what a is, we need to write down what these, before replacing u in equation 1 with f, we need to determine what these spatial and temporal derivatives will become. So let's just try the harder one first. So d by dy. So d by dy is essentially d by d eta by d y. We see that d eta by dy is t to the a, so that means that this will be t to the a d by d eta. Similarly, I can get that d2 by dy squared will become t to the 2a d2 by d eta squared. And, well, the other one that I need to know is d by dt. And d by dt is d by d eta by dt. And d eta by dt is a y t a to the minus 1, t to the a minus 1. So this is going to be a y t to the a minus 1, and then the d by d eta. And that's it. So we're all set. With these three equalities, we can just replace in this equation. Okay. So equation 1 then becomes, I've got du by dt here, and this du by dt is going to give me this sort of expression for f. So I'm going to have a yt to the a minus 1 df by d eta, and that's going to be equal to the right hand side of to nu, and the second derivative with respect to y, so that gives me t to the 2a d2f by d eta squared. Okay, so because it's dragging all these these derivatives along, because f is only a function of eta, I'm just going to introduce df by d eta to be f prime. So let me just rewrite this in a bit of a nicer way by essentially isolating the highest derivative onto the left hand side. So I've got f double prime, which is this guy here, and I need to divide everything by nu t to the 2a. So that gives me y t to the minus a minus 1 over nu f prime. Okay, so I've got that reduced equation. And now for my similarity variable, so my similarity solution method to work, what I need to have is to get rid of the y and the t dependencies of that equation. That equation should only be dependent on the quantity eta. And eta is fine everywhere. We have no other variable except in that term where we have y times t to the minus a minus 1. So we need to combine this y t to the a minus 1 into something that can be expressed only with eta. And so if you remember what eta is, it's y t to the a there's a y here. So what we want here is that this group y to the minus 8 minus 1 be equal to eta, right? So for the similarity method to work, we need a t to the minus a minus 1 to be equal to eta. So now if I replace eta here with its definition there, what I have is yt to the minus a minus 1 equals yt to the a. And well, this is effectively only, this is only valid for a equals minus 1/2. So that gives us that a equals minus 1/2. So based on this, right, we now have an exact definition, well, a completely determined definition for eta, which is yt to the minus 1/2. And well, therefore we can solve this equation, which then writes. So let me just write 2, and 2 becomes f double prime equals. So a is minus 1/2, so I've got a minus here. That guy here became eta to new f prime. And that is effectively now the solution that I need to solve for. Okay? So to solve for this, well, let's just first introduce w to be f prime. And so well, the equation that we were to solve now writes w prime equals minus eta over 2 nu w. Well, that's easily integrated into w equals a constant of integration times the exponential of minus eta squared over 4 nu. Okay, so this is our first line of integration. And remember that w is f prime, so we need to integrate this further to get back to f. And so, well, an expression for this would be to say that f is k1 times the integral from 0 to eta of that function, which is exponential minus eta squared over 4 nu. This is to be integrated over eta plus a constant of integration. Okay, so to be really rigorous here, what I should be, for this expression to be making more sense, what I should be writing is rather that it's k1 times the integral from 0 to eta of the exponential, and let's just write this down as minus gamma squared over 4 nu d gamma plus k2. And I'm just changing here to indicate the fact that this boundary of integration is the eta, whereas this eta that we wrote here is the constant over which we integrate this, is the variable over which we integrate this function. Okay, so this is an unambiguous writing for this expression. Okay, so now that we have this, expression, we need to find what this integral is equal to, and I'm going to write this. No, that's going to be 3. I'm going to write this equation here. I'm going to keep it aside for now. What I notice here, and that's what is important, is that I'm integrating an exponential of something that is minus the variable of integration squared. And that should directly remind us of a very classical function in mathematics, which is the error function. So let's remember that the definition of this error function, the error function for variable x is defined in the following fashion. It's 2 divided by the square root of pi times the integral from 0 to x of the exponential of minus y squared dy. It's a function that comes out a lot in probabilities or in classical physics, for instance. Okay, so now what we want is that expression here and to look like this one. And so we need to proceed to some changes of variables. So let's substitute. First of all, what we want is this guy to be the same as this guy. So we're gonna substitute y for gamma over 2 square root of nu. All right. And well, you know, what we have here is if we substitute that, then dy becomes d gamma over 2 square root of nu, of course. So what that gives us, if we substitute, is that the definition of the error function still for x is 2 over square root of pi. And then I'm integrating from 0 to x of the exponential of minus gamma, so it's y squared, so minus gamma squared over 4 nu times d gamma over 2 square root of nu. And actually, by writing this, I've made a mistake. Because I'm no longer integrating with respect to y. Y was going from 0 to x. Now I'm integrating with respect to gamma. So if y goes from 0 to x, gamma goes from 0. Okay, that boundary of integration is correct. But it doesn't go to x, it goes to 2 square root of nu x. So I forgot a 2 square root of nu here. Okay? So now I've rephrased this, this error function in this form. And well, this is pretty nice. Okay, we can just clean it out a bit by just taking out this 2 square root of n out, square root of nu outside, this boundary of integration, outside the integration. But what is different is that we should integrate from 0 to nu, and I have here x times 2 square root, sorry, eta, and I've got here x times 2 square root of nu. So I need to proceed to another change of variable, which is substituting. This time I need to substitute eta for 2 square root of nu x. Okay? And so if I substitute eta for 2 square root of nu x, x is eta over 2 square root of nu, right? So now my error function is the error function of eta over 2 square root of nu, and it's equal here, so I'm just cancelling out these 2's. Number 1 over square root of nu pi. And this is my integral here, 0 to, that becomes an eta, exponential of minus gamma squared over 4 nu d gamma. Okay? So that gives me that, that expression. And well, lo and behold, what you see here is the same expression as there, except for that parameter here. So what we can do is replace this expression in equation number 3. And so if we take 3 and replace with now what we found to be the error function in our case, what we have is that it's f equals, so we have k1 times square root of nu pi, that integral, which is the error function applied at eta over 2 square root of nu. And we still have this k2 constant of integration. Okay. Well, we can rewrite this if we want in the original variable of the problem. So in terms of u, and well, the only difference is that it's no longer f. It was a function of eta. U is a function of y and t, and the relationship between eta and y and t is given here. So that's k1 square root of nu pi erf of, that becomes y over 2 square root of nu t plus k2. And from this point, we can apply the boundary conditions. The boundary conditions give us that that u equals capital U at y equals 0. So at y equals 0, u equals capital U. means that, well, the error function at 0 is 0. So k2 equals capital U. That is the first constant of integration that is set. And the second one was the limits when y tends to infinity of u equals 0. And that's, well, when y tends to infinity, the error function is 1, and this is u. So what we have here is that k1 square root of nu pi equals minus u. And then I can just replace all this in and get that my velocity is factoring everything by u. It's u1 minus the error function of y over 2 square root of nu t. And this is the ultimate solution to Stokes' first problem.
This concludes this video on the solution of Stokes' first problem.